Thank you. Okay, so good morning, and thank you very much for introduction. I'm Mikito Koshino in Osaka University, and I'm a theoretical condensed matter physicist. And I'm also one of the people who is fascinated by the Hofstadter butterfly. And actually, I was born in exactly the year 1975. The same year, maybe Professor Doug Hofstadter is working on this machine here in Regensburg. And today, basically, I'm working on the graphene, on the quantum Hall effect, also topological material. And today, I want to introduce some of recent works which is closely related to the Hofstadter butterfly. So the one is about the Hofstadter butterfly in Moire superlattice. And as Professor Weiss mentioned at the end of his talk, I showed some different way to realize the Hofstadter butterfly. So this is called Moire superlattices. So I showed some theoretical work, and also that we have the collaboration with experimental groups, which actually realized Hofstadter butterfly in this system. And the latter half is about it's totally different topics. So this is old work. This is my PhD study back to 2001, and I'm going to show it's completely different. But Hofstadter butterfly, but appears in three-dimensional system. Okay, so let's start with this famous picture. The Hofstadter butterfly is like this. So we need two things. So the one is two-dimensional electron in magnetic field. So it gives the Landau levels. And another factor is a periodic potential, which is periodic in both in x and y direction. And then the energy spectrum is separated in the intricate fractal structure against the amplitude of magnetic field. Okay? So this is characterized by the flux penetrating the unit cell. And as many speakers already stressed, so to observe the Hofstadter butterfly, we need a condition of this condition, which says that number of magnetic flux per unit cell is the order of quantized magnetic flux, h over E. Okay? So for example, so the easiest way one can imagine is just use the usual atomic lattice. So of course, the crystal is a periodic array of atoms, so that we can we can use this period. But the problem is that this distance is very, very small, which is the order of angstrom. So it always gives a ridiculously strong magnetic field, which is required at the Hofstadter butterfly. So for example, it's like the 100,000 Tesla, which is of course not feasible in real material. So to overcome this situation, so the one possible way is artificially create engineered periodic potential, which has a much larger period than the atomic scale. You know, as Professor Weiss already showed, it was done in 20 years ago in a semiconducting heterostructure. They actually create atomic potential, of which period is about 100 nanometers, and then the Hofstadter butterfly feature actually observed for the first time. Okay, so now we do some different things. So that we use this Moire pattern. Moire pattern is a very general term, which is a long period beating pattern which appears in the competition between the slightly different periodicities. So for example, in daily life, we can see this kind of modulation. And this occurs because the period of this front plate, for example, in this case, and it's darting back slightly differs because the distance is different. And we catch the long period in the eye in this case. So now we want to use this. So of course, but we need to do this in nanoscale material. So we use graphene. Okay? So graphene is a two-dimensional material. Of course, just single graphene is not enough because of this period is again atomic scale. So we have two graphene layers, and for example, just stacked, but with some rotation. For example, you can imagine take two graphene layers and tilt one layer just by, say, 1 or 2 degrees with respect to the other, then we have a slightly different lattice period in layer 1 and layer 2. Then we get a beating. So beating is coming from the difference between the wave vector of a layer 1 and layer 2. And when they are too close, then we get very, very small k vector difference. And wavelength is the inverse of this, so that's why we get a very large period. So for example, we have this. Also, we can do that in graphene and other materials. So there is a material, so-called hexagonal boron nitride, we call HBN. So this is not carbon material, but this is consisting of boron atoms and the nitrogen atoms, and the B and N are arranged in honeycomb lattice in alternating pattern. Okay, B and B and B and. So it's like this. But it's, of course, different material from graphene. So it has a slightly different lattice period. It's the same honeycomb lattice. So that we don't need rotation in this case. When graphene, this blue one is graphene, and the orange one is hexabian. When two are stacked in a parallel way without rotation, then we have some modulation because of the lattice period difference. Okay? So we have a more pattern in many different cases. And we want to use this big period. So this period can be much longer than the original atomic period. So that this may open a way to observe the Hofstadter butterfly spectrum in magnetic field. Okay, so this is the story. So let's start with a twisted bilayer graphene. This is graphene rotated bilayer. So as you see, this the theta equals 0. Nothing happens. So that's because this is just parallel graphene. But if you tilt, we have some Moire structure. So maybe it's easier to go from the large theta side to 0. Then you see that this Moire pattern, a period of Moire pattern is like A over theta, for example. So it's inversely proportional to the angle. So that when you decrease this angle, then the period goes becomes larger and larger, and it goes to infinity. So it was noticed in the early stage in the graphene study. So this is epitaxial graphene, and the graphite and the graphene layers stacked in irregular ways, and they sometimes see this beating pattern. So this was noticed a long time. So now we want to use it for the Hofstadter butterfly. Okay, so now we are theorists. So we want to calculate the band structure of this system. But now that we immediately noticed that this is not so easy as we initially imagined. So this is the example of a typical twisted bilayer graphene. So say just stack graphene layer in some certain angle. Then we can notice that it is obviously we have some Moire period. It's obvious. But if you take two units and compare, but they are not identical in atomic scale sense. So for example, this you compare here and here, So this, it's not identical. So the arrangement of, for example, these two atoms is different of the two atoms. So this is because a Moire period is like this L over theta is not, of course, it's not always the multiple of the original lattice period. So it's always incommensurate. So if you take two graphene layers and just stack it into some random angle, then we always have this incommensurate problem. So this system doesn't have any rigorous period. So that means that we cannot calculate the band structure. We cannot define the unit cell, so that we cannot use the Bloch theorem, so that nothing can apply to this system. So that this is so difficult. So it's infinite. But fortunately, there's one theoretical treatment which avoid this difficulty. Actually, when the angle is relatively small, then the Moire beating pattern is much, much longer than the real original lattice atomic period. Then we can show that we can't forget about this lattice period. Then we just can extract this long period Moire pattern. Actually, the low energy spectra is determined, basically almost 100% determined by this long range physics, so that we can forget this small period. So that this is coarse graining. So that we do some coarse graining to extract the long wave components. So what we do is, this is simple. So of course, there are a lot of equation behind this slide, but I just showed in some intuitive part. So this is an example with a small twist angle. Now, if you look at some certain part, then it looks like, for example, this part really looks like it's just parallel graphene without any rotation. Okay, so it resembles. But if you go to some other point, but it's like this. But it's again resembled some non-rotated bilayer graphene, but with some certain parallel shift, so delta. So that we can view this system as the locally non-rotated graphene, but this delta, so this parallel translation slowly depends on the position. Actually, so here we had the delta equals 0, but delta is slightly increasing. And it depends on R in a certain way. So this is the starting point. And non-rotated bilayer graphene, it's easy to have derive the Hamiltonians because this is a periodic system. So the important thing is the interlayer coupling. So the intra-layer is just graphene, so that we know very well. So the problem is how the layer 1 and layer 2 are interconnected in the Hamiltonian. So this is U matrix. So U matrix is approximately given by this non-rotated part. This delta is this shift, and this is treated as a parameter. Okay? So that we can think about this. This can be derived in an easy way. And then the delta replaced with the delta with some position-dependent delta R. Then we go to this system. So this is the rough idea. Of course, there are a lot of mathematics which verifies this approximation. Okay? So this is the result. So we first, the original system has this is an incommensurate system. So it's consisting of an infinite number of atoms. So the Hamiltonian has an infinite dimension. But by doing this coarse graining, we end up with a very beautiful Hamiltonian. This is a simple Hamiltonian, which is 4x4 Hamiltonian. So one part is this is Dirac cone of the graphene layer 1. This is the graphene layer 2, and this is the U of delta of R. Is this is our coming from our recipe. So then honeycomb lattice. This is written by like this. Omega is some complex number, but this is very simple. Okay. So now before going to the magnetic field stuff, let's calculate the energy band, and it's already interesting. So for example, it shows the band structure at different rotating angles. So this is 4 degree, 2 degree, 1 degree, then that Moire period goes, actually increases from this side to that side. And this is the energy versus some K wave number. And in relatively large angle, we still see some remnant of Dirac cones, which is from the original graphene. But in a small angle, so we see totally different things. So that actually Dirac cones are smashed in the energy scale, that we have almost nearly flat energy band. So this is because in small angle, we have a long range period. Then it gives a low energy part. It's strongly modifies the low energy part because so typical wave number is just 1 over a wavelength. So it's more and more important in the low energy part. So this is why we already have a very, very funny thing around the charge neutrality point. Okay, so now a magnetic field. So that we have 2 graphene layers up and down. And of course, if we don't have any coupling between 2 layers, we just have lambda levels as a function B. So in this case, linear band gives a square root behavior, but it's very well known. So of course, we have the same thing in the lower band. Now we couple 2 lambda levels by U of delta of R. So this is what we did. So for example, we can show that this is an energy spectrum of a large angle, 9.43, and we get actually the usual lambda, just lambda level. This is just a layer 1 and layer 2 are completely degenerate. So it's just boring. So this color shows the quantized Hall conductivity, which was already mentioned by the Professor Weiss, also Professor Wigner. And the Hall conductivity is quantized when your Fermi energy is inside this energy region. So this 4 means 4 times minus E squared over H. Okay, so this is just lambda level because it's not surprising. Now our 9.43 degree unit cell is very, very small. So that means corresponding K wave is very big. So we have some subband structure far away in the energy scale. So then around this scale, so we have just Dirac cones. This shows the band structure at 0 Tesla. So that's why we have just lambda level. So, but in going to a lower angle side, then now we have this. So now that many strange coupling subband structure actually coming down to the energy scale of our interest. This is zero field case. And this is the energy versus a magnetic field. We obviously see the Hofstadter butterfly structure. So we have 4 and minus. So this color shows, again, the whole conductivity. So for example, this is like coming continuously connected to the original lambda level of graphene. But we have some new feature which is coming down from the certain energy. So this is corresponding to the lambda level of this pocket, actually. We have some hole-like pocket. And we have the same thing here. So the electron region branch and this whole branch meet together and they interfere, and it gives some recursive structure. So this is that we actually see the Hofstadter butterfly moire system. Okay, so virtue of this is, of course, we can get a larger period. Which is needed to realize a Hofstadter butterfly in a real system. So as I said, if you use the atomic lattice, required beads like this. But now, so this scale is like the order of 10 nanometers. It's much bigger, 100 times bigger than this. Of course, and this period can be, however large as you like, because if your angle goes to 0, then this is just infinite. Okay, so then for example, if A equals 10 nanometer, we get B equals 10 Tesla, because flux is proportional to A squared. This is area. So that when you increase the A lattice constant, then the required magnetic field rapidly decreases. So the B equals 10 Tesla. So now this, okay, so now I'm going to show the collaboration with experimentalists. But the first one was done not in graphene system, but in a graphene boron nitride system. So let me show you this new system. And graphene boron nitride, and as I said, boron nitride is composed of a boron and an atom, nitrogen atom, and it has a honeycomb lattice. But the length scale is a little bit, atomic constant is about 1.8% larger than graphene. Then we get moire. And yes, so we can do the same thing again, theoretically. So the graphene case, the moire is generated by the rotation. But in the graphene boron nitride, so it's generated by expansion because of the lattice constant difference. Of course, we can combine with the rotation with it, but with zero rotation, this is just expansion. Then we get delta of R. So then all the treatment is all the same. So we again end up with 4x4 Hamiltonian, but now this first layer is graphene, of course, but second layer is BN. And hexa-BN is not Dirac cone. It's not metal, but this is this insulator. It has a large energy gap, as big as 5 electron volt. So it's like this. So the low energy spectra is dominated by just graphene electron, but it feels the effective potential of hexa-BN. So this is the calculated band structure. So the original Dirac cone is folded into the Brillouin zone, or superlattice Brillouin zone of moire, and somehow we have a larger gap in the negative energy side by the positive energy side. So this is actually very much, pretty much agree with a conductivity measurement in the experiment. Okay, so I want to say that this is again described by the 4x4 Hamiltonian. Okay, so again, we also can include a magnetic field, then it gives a Hofstadter butterfly. So we have a big, larger structure in the whole side. So we have Hofstadter, the fractal pattern is more obvious in the whole side than in the electron side. But anyway, we have this. Okay, then we collaborate with some experimental group in Colombia and also MIT, and they actually succeeded to measure the feature of a Hofstadter butterfly in the moire system. Also, there are first 3 papers, and one of them is a Manchester group, and I think this is introduced by the Professor Voloja Falco in the next talk. Okay, so let me explain what they actually observed. Okay, so for example, this is the MIT one. So they always plot like this. They actually, in this case, they measure the conductance of a whole bar, and this is the color chart of conductance as a function. This is a gate voltage. That means the number of electrons, carrier density. Or so this is has a 1-to-1 correspondence to the Fermi energy. So when you go the larger VG means a larger number of electrons. So that means a higher Fermi energy. So this is a negative Fermi energy, for example. So this is the magnetic field. So now it's vertical. So they always see the deep structure which corresponds to the gap of energy spectrum in this way. Okay? So they have some fan-like structure which is centered in several different points in n-axis, this electron density. So this is this. So without superlattice potential, I mean without hexa-BN, when you have just graphene, then we have just a Landau level of graphene. Then this is it. Okay, so this usual Landau fan. But if we have a superlattice potential, we have some other series centered at some different point. So this 4, or 0 to 4, this distance in the electron density actually corresponds to the number of electrons per one superlattice Bloch band. So that's directly related to the period of superlattice. And we can show that so that this intercept of the old line is integer quantized in N0 in this case. And also that this gradient is also quantized. This corresponds to the whole conductivity. Okay? And we have many lines, and we also have okay, so those Landau fund, the different Landau fund crosses at a certain point, and this gives always gives some fraction in the magnetic field. So this corresponds to the one of P over Q in the Hofstadter butterfly. Okay, so and we actually in the experiment we see some structure corresponding to the crossing point of those different series of Landau fund, and this is called Zach oscillation. So they see, and also we see some second generator of Landau. This is related to fractal nature. So this is not zero magnetic field anymore, but we can see that some Landau fund-like structure centered to some point which is not zero magnetic field. This is some second generation, so they clearly see that. So that this is it. So of course, in the real system, as Professor Hofstadter stressed, so we also have some disorder effect or temperature, and so that it smears out a higher generation. But of course, we have many of those effects in the system as well, but we see that at least we have the second generation. This is some remnant of fractal nature. Okay? There are also some other, so this is other experiment, so they have basically the same thing. So for example, if you go from here to there and fix the electron density and change the magnetic field, and they see the fractal nature again. So this is the main Dirac Landau level. This is a whole conductivity. This experiment measuring whole conductivity, and we again have the second generation, maybe here and so on. So that it is all clear. There was another thing is that the gradient of line corresponds to the whole conductivity, and they actually measure the whole conductivity at this point, and they actually, it coincides with gradient. So the gradient of this curve and the whole conductivity are totally independent experimental information, and they coincide. So that means that Thouless-Como TKNN formula, which is a formula for whole conductivity in the Hofstadter butterfly, is experimentally verified. Okay, so this is the brief explanation of what the first two first experiments showed. Okay, so let me. It's how much time? So I briefly explain the three-dimensional Hofstadter butterfly. I think it takes 5 minutes. The Hofstadter butterfly is usually conceived in peculiar to two-dimensional, not a system. But in my PhD work, I showed following. So we think about an array of one-dimensional chain, for example. So it's a tight binding model, actually. But this is very, very anisotropic. This is very conductive. So say the hopping is very strong in this direction, but they are weakly coupled. So different chains are weakly coupled. So for example, you can think about a tight binding model of hopping integral is biggest in this direction, but perpendicularly it's just 10 times smaller or something like that. Then apply the magnetic field parallel to the line for a certain angle, and I get this. Okay? So the Hofstadter butterfly appears. Okay, so the first side, okay, so this is kind of some kind of extension of a two-dimensional Hofstadter butterfly, because it looks like this is we have line here, but we have a lattice, x and y direction, so it's kind of a two-dimensional lattice. But this is different because magnetic field is now it's not perpendicular to this plane, but it's parallel to the plane. Okay? Also, the biggest difference is the horizontal axis. In the usual Hofstadter butterfly is plotted against the magnetic field amplitude, but this is plotted against the angle. So we tilt fix the magnetic field amplitude and tilt the angle from the y direction to z direction, then we get this Hofstadter butterfly, which apparently looks very similar to 2D butterfly, but it's somewhat different. So that I should explain why this happens. The origin of two-dimensional Hofstadter butterfly spectrum is coming from the competition of two different periods. So in this case, this original 2D butterfly. So band structure, and when you have a periodic potential in x and y direction, then we get a band structure. And this is, of course, the density of state is separated in the unit of 1 over a square. So this is the number of electrons which is accommodated in one single Bloch band. And on the other hand, in magnetic field, so this is the unit is different. So the electronic state is packed in the unit of EB over H, which is proportional to B. Okay? So they are competing. So the ratio is actually this gives the P over Q. The ratio does matter. And the important thing is this is related to the magnetic field. So if you tune the magnetic field amplitude, then this P over Q actually runs in the continuum axis. So this gives the Hofstadter butterfly. P over Q gives the changing dramatic way, then we get a Hofstadter butterfly. So now the three-dimensional system is totally different. So this is a three-dimensional system. It's conductive in this direction. And they are weakly coupled. So we have some kind of 2D plane in here and here. And the magnetic field is tilted, so that we have two magnetic field component, which is perpendicular to this plane, and the other is perpendicular to that plane. And of course, they give the different n lambda in this system. Okay, so the NZX means giving the Landau quantization corresponding to this field, and the other is this field. And again, when changing the angle, then this ratio actually, of course, it runs in the continuum axis. So that's why we have a Hofstadter butterfly. So this is very, very different things. The most important thing is we need a magnetic, so 2D case is directly related to the magnetic field amplitudes. And then we need a high magnetic field. But we don't need very high magnetic field in this case because this is just tangent theta. Okay? So we can show that in actual material how much field is required. It's the order of 10 Tesla I can show. Okay? So there is some relationship. This is phi as 2D, and this is theta in the 3D. And this is not the end of the story. So I have quantum Hall effect. Okay. So the Hofstadter butterfly is another thing, interesting point of Hofstadter butterfly is they are related to the quantized number, Chern number. So this is already shown in Professor Weiss's talk, and when you have your Fermi energy inside any of those intricate gaps, then the whole conductivity is quantized in some way. This N is written here. So you already saw this in the graphene this twisted bilayer graphene case. So I wanted to show what happened in three-dimensional butterfly. Okay, so this is the answer. So now this is a three-dimensional system. So the quantized whole conductivity is a tensor. So that we have three different components: sigma xy and yz and zx. And the two of them are actually quantized in the gap, like this. So this is another thing. So the three-dimensional, this is some actual realization of a three-dimensional quantum Hall effect, which was realized in an old paper. So if you have a lattice and you have magnetic field a certain way, and so this paper, this is a general argument. It says that if you have a real energy gap in the spectrum, then the whole conductivity must be quantized. We have three integers, then we have N1, N2, and N3. So in this case, actually N3 is 0, so we are left with only two integers. But this is the interesting example of the three-dimensional whole conductivity. Okay. So that's it. So my message that we can realize that Hofstadter butterfly in two different ways. One is that this is more why I use more spectra, but this is a rather classical original two-dimensional Hofstadter butterflies. And the latter half we showed some different Hofstadter butterfly peculiar to 3D. Okay, thank you very much for your attention.
Is there a system inside where one can probe the three-dimensional Hofstadter butterfly?
Sorry?
Is there a system inside?
System inside? What do you mean system?
I mean a crystal with corresponding period which could be probed experimentally.
Classical.
I mean, to resolve this structure, I guess you need magnetic fields.
Yeah. Is
there a system which could be explored with lower magnetic field strengths?
Actual system, you mean? So I think the closest system is okay. So the organic semiconductor, which is a TMTSF, and this is a chain-like structure. This is quite a one-dimensional system. We have chains, and they are coupled and weakly. But they don't see this because problem is we have chain, but the coupling strength between y direction and z direction is again very different. So this is very anisotropic in the y and z direction as well. So in this case, we need to have a fairly equal coupling. In the original Hofstadter butterfly, for example, so we have Tx and Ty, and if you differentiate in Tx and Ty, and it's rapidly blurred. The same thing has happened. So we need some chain-like structure and then the isotropic hopping in the two direction. Yeah.
Let's continue. Thank you very much.
Okay, thank you.